Wildfires are a growing global problem, and in the recent years we witnessed some of the worst wildfires on record. Some of the recent examples include the 2018 Camp Fire, 2019 Australian bushfire season, or the 2020 wildfire season in California and the western coast of the United States. UAVs or drones are a potentially very appealing platform for wildfire surveillance. Currently, their use is very limited due to lack of autonomy, limited range, high cost, and most importantly, the lack of onboard perception systems. That's why in this demo, we present a system to address that gap. Our system is composed of an autonomous drone deployed at a remote site, and the fire perception box, the multimodal drone payload capable of fully onboard fire detection that can send real-time updates to the base station via the telemetry link. The fire perception box is the hardware necessary to enable multimodal fire perception, as well as realize the autonomous control of the UAV via Mavlink protocol. The device features a Sony IMX219 sensor, a Lepton 3.5 radiometric infrared camera, and a Jetson Nano computer with an embedded GPU. The payload connects to the drone via a standard Mavlink connector. The hardware is also open source, so anyone who desires can go to the link in the video and interact with a 3D model, as well as download the files necessary for 3D printing and replicating the device. On board the UAV, we realize 6 different perception tasks. The perception tasks are divided into classification and fine-grained localization. The tasks in classification are RGB image classification, infrared image classification, fused RGB and infrared image part classification, and tasks in fine-grained localization are RGB heat maps localization via GradCam process, infrared spectrum hotspot segmentation, and infrared plus RGB heat map fusion. The software pipeline for realizing the perception tasks is shown on the left-hand side, and the latency of the entire system as measured using fire perception box hardware is 49 milliseconds, which corresponds to the throughput of 20 frames per second. This includes all the overhead from camera I/O and thread synchronization. On the screen we can see a video from a real-world wildfire scenario with a heat map overlay on it. The heat map overlay is produced using GradCam process, and the areas of the heat map that are shifted towards red come from the areas where neurons in the feature maps were highly excited and had highly positive gradient, which corresponded to high impact on the final classification score. In other words, these areas look more fire-like to the network, and on the opposite side, the areas shifted to blue look the least fire-like to the network. Our fire detection approach has accuracy of 97.5% as measured on the test split of our own dataset, 95.8% as measured on the test split of the external Dunnings dataset, and 94.4% as measured in a real-world fire scenario in the field. Finally, we show a fused infrared and RGB classification approach that allows us to raise accuracy of the detection by 1.4 percentage points, as well as increase the recall score by 6 percentage points. Future work includes creating real-time wildfire maps with the system, as well as adding a reinforcement learning path planning component to the UAV.